Now let us find the time domain and frequency domain analysis of the sampling process here. First I will see a signal in time domain. I will consider as an arbitrary signal of the shape. It is an arbitrary signal. So the shape is considered like this. The assumption as per the Nyquist condition is it should have a band limited in nature. That means it should have the highest frequency component, some FM. Let us consider this shape. So this is not a restriction on us to assume a triangular shape of this signal. Only thing is it is convenient to assume a triangular shape while we are considering the spectral analysis of this process. But there is no restriction on this signal to consider a triangular shape in frequency domain. Only thing is here the condition is it should have some highest frequency component because it is band limited in nature. So we are considering this signal which is band limited to FM, and a triangular shape we have assumed arbitrarily. Fine. To get the sampled version of this signal, what we are doing means we are multiplying with a train of impulse signals. Here a train of impulse signals means a series of impulse functions which are spacing each one Ts duration apart. Observe that the amplitude I am considering as this delta train, amplitude is 1, and each sample or each delta function is spaced between them Ts, 2 Ts here and minus Ts, minus 2 Ts and so on. So after multiplying this x of t with the delta train, what the signal we are getting in the result of multiplication of these two in time domain, if we observe, let us take this one as sampled signal xs of t, which is we have considered that multiplication of these two signals, that is x of t multiplied with this del t of t. Observe two different signals multiplied here, but out of which one is a delta function is there. If we remember x of t, whenever it is multiplied with del of t minus t naught, from the sampling property of the impulse function, we know that it is equal to x of t naught multiplied by delta function. So what happened after multiplication of a signal with the delta function means we know that the delta function will be there itself, but the amplitude of the delta function will become the instantaneous amplitude of this multiplicand signal. So this is the expression we have from the properties of the delta function. So from that we can observe whenever this x of t multiplied with the train of impulse functions, each delta function will be there itself, but the amplitudes going to the corresponding amplitude of the multiplicand signal. This amplitude will go to this amplitude, and this origin amplitude will go to this one, and this amplitude will go to this amplitude. Like this, we will get different amplitudes of this delta functions as per this property. So that we will get finally the sampled signal in this shape. So delta functions will get at their respective locations with the corresponding amplitudes as per the x of t instantaneous amplitudes, like this as shown in this figure, and here spacing between the delta functions same. So this is drawn from the property of impulse function, this one, sampling property of the impulse delta function. Fine. Let us find the frequency domain analysis of these two signals. And in Fourier transforms we have derived the Fourier transform of a periodic function should be, observe here, signal is periodic in nature. The signal is periodic in nature. Any arbitrary periodic signal should have the Fourier transform, a delta train, and already it is a delta train. Delta train Fourier transform also, delta train we have discussed, and we got that the delta train in frequency domain having the delta functions each spaced apart at fs, where fs is equal to 1 by ts. This is 1 by ts, and the amplitude of this function also fs we know. So this is what we have derived in the Fourier transforms. So let us consider the frequency domain representation of this delta train. Here delta train in frequency domain let us represent as delta t in F analysis. So observe here, this is a delta train, this is also a delta train, a train of impulse functions. Only difference is here, these two spacing Ts and two spacing is here Fs. Relation between this Ts and Fs is, Fs should be equal to 1 by Ts. And let us represent this delta function, sum of impulse functions like this. Here k values of minus infinity to plus infinity, it is del of f minus k Fs. Similarly, we can represent this train of impulse functions in time domain. We can represent like this. This del t of t is equal to sum of all impulse functions. Let us take n value from minus infinity to plus infinity, del of t minus n ts. So sum of impulse functions, this one and this one also we have sum of impulse functions from minus infinity to plus infinity. Anyway, the Fourier transform of this function, which is a sampled signal, that is nothing but multiplication of these two signals in time domain. Once the two signals are multiplied in time domain, we know that the corresponding Fourier transform should have convolution in the frequency domain. That is from the properties of the Fourier transform. We have that convolution in one domain resulting into the multiplication in other domain, or multiplication in one domain resulting into convolution in other domain. From that, we can plot the frequency domain representation of this sampled signal by taking the convolution property of the delta function. I'll write the convolution property of the delta function here. Del of t minus t naught, if it is convolution with some x of t, that should be x of t minus t naught. Right. This is what the convolution property of the delta function. That means if x of f convolution with some delta function, we should get x of f minus fs. What we can observe here means, when x of f convolution with some delta function which is located at fs, then this spectrum should be shifted to that fs. Right. An impulse function does not exist at that location. After convolution, impulse function should not exist, and the multiplicand signal is shifting to that impulse signal location. That is what the convolution property of the delta function we have. According to that property, each delta function here, if it is convolution with this spectrum should be shifted to corresponding delta function like this. So a series of this x of f spectrums will get. So first, whenever this delta function convolution with this x of f, we will get the spectrum here. Let us consider this is fm, this is minus fm. And then whenever this spectrum convolution with this delta function, it should be shifting to this location fs as per this property. So that we can take at fs, we will get this second function like this. And here of course fs is the amplitude of this function, 1 is the amplitude of this function. So that here also you will get fs amplitude. And then this spectral components, if you observe, this should be fs plus fm, this should be fs minus fm, because here total width of this spectrum should be 2fm. So here also it should be 2fm, because the spectrum only shifting, there is no scaling on that. That's why this is fs plus fm and this should be fs minus fm. Similarly, the spectrum, whenever it is convolution with this function, we will get the corresponding shifted version here at 2fs. So that this is 2fs plus fm and this component 2fs minus fm. And we can plot remaining all functions. This is a periodic function like this. So this is the spectrum of the sampled signal. Observe, this is multiplication of these two signals. So obviously the corresponding Fourier transform should be convolution of those two functions x of f convolution with del t of f, where del t of f is nothing but sum of infinite number of impulse functions. So this is what the spectrum of the sampled signal. So according to the sampling theorem process, a signal which is band limited to fm can be completely reconstructed with the knowledge of its samples uniformly taken at the rate of 2 fm samples per second, right? So if in this case this frequency fs is greater than or equal to 2 fm, then what is the sampling theorem says? That means with the knowledge of its samples, we can completely reconstruct this x of t. That means, if we get this signal, sampled signal, we should get this x of f from this sampled signal. For that, what we can do means, to reconstruct this x of f original signal from the sampled signal, we will pass this signal through a low pass filter of appropriate cutoff frequency here. So that this low pass filter or reconstruction filter will attenuate all other high frequency components, and the low pass filter output will be this function, which is nothing but x of f. So what we are getting means here, the low pass filter output is having highest frequency component Fm, and this is nothing but x of f, which is the original signal we have considered for sampling purpose. Like that, we can reconstruct the original signal from the sampled signal by using a reconstruction filter, a low pass filter of appropriate cutoff frequency here. So if you observe here, as per the sampling process, whenever Fs is greater than 2Fm, we are taking as oversampling case. Whenever Fs is equal to 2Fm, we are taking as critical sampling, and if Fs value less than 2Fm, we are taking it as undersampling. As per the Nyquist condition, Fs should be greater or equal to Fm, or oversampling, critical sampling is preferred for sampling process, but undersampling is an invalid condition for sampling process where Fs is less than 2Fm. If you observe this graph, here Fs minus Fm, this frequency component is plotted more than Fm, right? Here Fs minus Fm is considered as greater than Fm. That means, if we take Fm that side, 2Fm that side, and Fs this side, that means Fs value greater than 2Fm. So what is the sample signal plot available here means, that is for Fs greater than 2Fm, or that is nothing but oversampling process. So this plot is for oversampling process. Similarly, we can plot this Fs minus Fm component exactly starting at Fm like this. Then we can consider that plot as critical sampling case, and if it is less than 2Fm, that means this component is less than Fm like this, then we will get spectral overlapping. Let us discuss one by one these issues.